Hello again, physics friends. Every now and then, it's helpful to have a very brief video to make sure that we don't fall down a trap of a misconception, okay? We talk a lot about net force. Net force is the sum of all forces on a system. We also talk about torque and net torque. And so it might be attractive to think that since the torque of a force is given by R cross F, you might like to think that the net torque is equal to R cross the net force. That is most certainly incorrect, and we want to spend a few minutes to point out all the ways, or some of the ways, some of the many ways, in which that cannot be true, okay? So the main takeaway here is you have to compute the torque for every force individually and then add up those torques to find the net torque. You cannot find the net force and then compute the torque for it. The first way that I think it's clear that you can't first find the net force and then do R cross F is there's not only one position vector, R. So let's say you have some object and you apply several forces to it. So I'll draw these forces here in purple. I'm going to apply a force like that. I'll call it F1. I'm going to apply a force like that. I'll call it F2. And maybe I'll apply a force like this. I'll call it F3. It doesn't really matter what these forces are in terms of length and direction, just that there's more than one force. And let's say that we have an origin. Remember, we always have to define our origin when we talk about torque and angular momentum. And then we ask the question, is the net torque equal to the net force crossed in with R? Well, number one, in the statement torque equals R cross F, what R is this, right? So we've got to be really explicit about that. This R is equal to the position vector to the force, to the point of application of force. Okay, so if you have three forces, in general, those will all happen at different locations. They will all be applied at different positions. So if you are tempted to say net torque equals R cross net force, well, what are you going to use for R? There's not one R, there's three different R's. So how are you going to decide what to use for this R? Okay, so from this example alone, you should see that this statement is problematic, and in fact, the statement is incorrect, okay? The right way to proceed is to say that the net torque is equal to the torque due to force 1 added with the torque due to the other forces, 2 and 3. And that would be the position vector to the first force crossed into the first force, added to the second position vector crossed to the second force, and so on. Okay, so first find the individual torques and then sum it up. Okay, here's another way to think about why we have to first figure out what the individual torques are before we find the net torque. Okay, it turns out you can have situations like the following. You can have a net force that's not zero, but you can have a net torque that's equal to 0. You can have a net force that's equal to 0, and you can have a net torque that's equal to 0. You can have all of these four possible combinations of non-zero and zero net forces and torques. So we could have neither of them equal to 0, and we could have one in which the net force is 0 and the net torque is not 0, okay? And so we'll go through and give an example of each of these, but if the net torque were equal to R cross F net, then this last case would certainly not be possible, because if your net force is 0, there would be 0 on the right-hand side here, and we'll show a situation where that does not necessarily lead to a net torque being 0. So I'm going to label these A through D, and we'll proceed to give one example of each, and then we'll wrap up. So let's start with case A. The net force is non-zero, but there's no net torque, okay? So there's many different examples of this. I'm just going to draw one. All of my cases are going to involve a circular object and two forces. Okay, so here I have, let's say, one force like so, and another force equal in magnitude like so. In fact, these are the same vectors, just applied at different locations. We have two different position vectors like so, and we're considering the center of this disk as our origin. Okay, what is the net force in this case? Well, it's equal to the sum of these two forces. So it's just 2 times any one of the forces because they're parallel to each other. What is the net torque in this case? Well, notice the top force is trying to make the disk rotate clockwise. The bottom force is trying to make the disk rotate counterclockwise. And by symmetry, those have to be given, those have to be providing the same torques, right? So if you remember, torque is R cross F, and we can do that on each of those two forces. Okay, so the net torque is going to be equal to R cross F, that is into the page. So let's give our, let's say that our disk has a radius of capital R. So we could say the top force produces a torque that's R cross F, or R times F, because R and F are perpendicular, into the page. And our second force is going to produce a torque that's R cross F, which ends up being capital R times capital F, because R and F are perpendicular, and that is out of the page. So if we were to assign, say, the z direction to be positive into page, then we would have a positive RF and a minus RF, and when you add those all up, you get a net torque of 0. Okay, so that's a situation where we have a net force, but not a net torque. Okay, how about situation B, which is asking us to find a scenario where we have a net force of 0 and a net torque of 0. Again, we're going to restrict ourselves to drawing circles with two forces on them, and we're going to take our origin to be in the center of the circle, like so. Well, one way forward here is to apply the forces radially outward in equal and opposite directions. Okay, so here we have F1 and we have F2, and both of those forces are acting on a diameter that goes through the middle of the circle. So Fnet is clearly 0 if F1 is equal to minus F2, if the forces are equal but opposite. Okay. How about the net torque? Well, not only is the net torque 0 in this case, but each individual torque is 0. How do I know each individual torque is 0? Well, I have R1 cross F1 and R2 cross F2, but R1 is parallel to F1, R2 is parallel to F2, so these individual torques are 0. Okay, so that's an example where you can have 0 net force and 0 torque. Moving on, item C, which is asking us for a non-zero net force and a non-zero net torque. Okay, so by now you know the drill. We're going to have a circle with an origin, and we're going to draw two force vectors on it. Let's draw one here and one here. Okay, we'll label the first one F1 and we'll label the second one F2. Those are acting at position vectors R1 and R2. Our net force is equal to F1 plus F2, the vectors, which is, if those two forces are equal to each other, we can call that 2F1 or 2F2. In other words, non-zero. That's all we care about, not 0. The net force, the net torque is R1 cross F1 plus R2 cross F2, the sum of the individual torques. okay? And let's be real explicit this time. Let's say that the z direction points out of the page. So a plus torque points out of the page and a minus torque points into the page. For force 1, we have R1 cross F1, that points into the page, so that's a negative torque, or torque in the negative z direction. So that would be minus capital R times mag F1 in the z hat direction. And how about R2 cross F2? Well, R2 and F2 are parallel, so that cross product is 0. So here we have a non-zero net torque as expected. Okay. So we have one remaining case, and that one remaining case I'll draw up here at the top right. We'll call that D. And for part D, we want a 0 net force, but a non-zero net torque. So again, you know the drill. We have, we have our disk, and we're going to draw two forces on that disk. I'll draw one up here, F1. I'll draw one down here, F2. Notice both of those forces want to make the disk rotate in the clockwise direction. So they're constructively contributing to the total torque. If F1 is equal and opposite to F2, then we have a net force of 0. And how about the net torque? Well, the net torque we have to do separately, torque 1 and torque 2. That's R1 cross F1 plus R2 cross F2, both vectors. And notice R1 points up to the point of contact for force 1, R2 down to the point of contact. Those vectors are perpendicular, R and F in both cases. R1 cross F1 is into page. R2 cross F2 also into page. So there's no way that those torques can cancel out. In fact, they're going to add together. And we decided into page, if the plus z direction was out of the page, into the page would be the minus z hat direction. And so the net torque is equal to 2 times the radius of the circle times either F1 or F2 because they're equal in magnitude in the z hat direction. Anyway, the bottom line is the net torque is non-zero. Okay, even though the net force is 0. So all of this is to say, do not fall into the trap of thinking that the net force is simply a position vector crossed into the net force. That can't be right. It can't be right just because there's no such thing as 1r, given multiple forces acting at different locations, number one. And also because, for example, you can have a non-zero net torque even if there's a 0 net force. Okay, so I promise I keep it short. I went maybe a little longer than I thought, but hopefully this has been illuminating as we practice writing out and working with torques and thinking about how a torque affects a system. Until next time, take care and be well.